Guys, so in one of my previous videos, someone asked me to explain what the pigeonhole principle is. So in this video, I'm going to exactly tell you what the statement of the pigeonhole principle is. I'm going to show you a proof for the pigeonhole principle, and then we'll see a question in which we'll apply the principle. So let's first of all go ahead and actually see what the pigeonhole principle is. So it says that let k be any positive natural number, and then assume that you have k plus 1 objects which are to be placed in exactly k containers. And then the pigeonhole principle states that in such a situation, there will be at least one box which will contain two or more objects. So the way to intuitively think about this principle is, let's say that you have 5 books that you want to place in 4 containers. Now what you can do is you can place one book in each of the container and you'll still have one book left over. And now irrespective of which box you place that book in, you will have at least one box which will contain two or more objects, or in this case, 2 books. So, but this is a theorem. It does require a formal proof. There are a lot of ways to prove it. You can write a proof by induction, a proof by contrapositive. In this question, I'll present a proof by contradiction. So what I'm going to do is, first of all, let's see. Let's just restate in a little bit of a different manner what this theorem states. So it says that if you have k plus 1 objects in k containers, where of course k is once again a positive natural number. I'm not gonna restate that over here, but this is what it's saying. It's saying that if you have k plus 1 objects in k containers, then there's at least one box or at least one container with two or more objects. Now its negation, or the opposite or the contradiction of this statement would be as follows. So its negation is as follows, that you have k plus 1 objects in k containers and all the containers have one or less than one, or I would just write down have less than one objects in it. Now notice that only one of these two statements can be true. Either this one can be true or either this one can be true. In other words, since one of them is the negation of the other, if one of them is true, then the other one must be false. So in this case, what I'll do is I'll show that the negation must be false. And well, if the negation is false, then this statement over here must be true, and that will prove the pigeonhole principle. So what I'm going to say is I'm going to say notice. This is the question that I'll talk about later on. So I'm going to say notice if all containers, or I would say all of the k containers, just to emphasize, all of the k containers have, this should be less than or equal to actually, have at most one object, then the maximum number of objects in all containers combined is at most k. K times 1, which is k, which is clearly a contradiction. As we have k plus 1 objects. Thus, the negation is false. And if the negation is false, then the original statement, that is, if we have k plus 1 objects in k containers implies that at least one container has two or more objects must be true, and that will complete the proof. Thus, the original statement must be true. I'm just going to write it down over here, must be true. And this will complete the proof. So the proof is quite simple. There is a way to prove this. The reasoning is quite simple or quite similar by using a proof by contrapositive. It will also work quite similarly. There's also this proof by induction that I came across. I also find that to be quite interesting, but I just find that to be unnecessarily long. I believe that this works just fine. So the theorem makes intuitive sense. It has a pretty neat proof to it as well. Now let's see exactly how we can use this theorem. Now I came across this question. It says, let P. It's a pretty nice question, and it actually does use it uses the pigeonhole principle in quite a neat way. So it says that let P1 all the way up to P of n plus 1 be n plus 1 distinct points inside a circle C, such that none of them are the center of C. And then let L1 all the way up to Ln plus 1 be the lines connecting the center and these points respectively. Prove that there are two distinct lines, Li and Lj, such that the smaller angle between them is at most 2 pi over n. So the question at first sight might seem quite difficult, but you'll see it has a pretty nice solution to it. The first thing, okay, at this point, of course, I would ask you to pause the video and see if you can do this question on your own. Of course, this question will use the pigeonhole principle in somehow, so see if you can solve this question on your own. So by now, I hope you guys have paused the video and attempted this question. So in this case, the first thing, of course, that you should always do is make sure you define all your variables. So in this case, I'm going to say let n be any natural number. Let n be any natural number. It can also be any positive natural number. It has to be a positive natural number because the angle should be at most 2 pi over n. It doesn't make sense to divide by 0. Of course, in this case, I'm assuming 0 is a natural number. That's an entirely different debate. Anyhow, so now n is a natural number, and we have exactly n plus 1 points. And we have to prove, and of course, these n plus 1 points are placed randomly in a circle, such that none of these points is actually the center of the circle. And what I want to show is, and then each of these points is joined to the center of the circle. Then I want to show that there are at least 2 points, or sorry, there are at least 2 lines, such that the angle between them is at most 2 pi over n. So the way I'm going to do that is I'm actually going to show a strategy. So what I'm going to say is that let's create a circle. And what we are going to do, so first of all, just to give you a basic idea, I'm going to divide this into 4 equal parts. Okay, so I'm going to divide this into 4 equal parts. Let's say that this is 4 equal parts. And so now what I'm going to do is I'm going to put 5 points in here. So I've divided it into 4 parts. In other words, I've divided it into, like generally speaking, I've divided it into n equal 4 parts. And now I'm going to place n plus 1 equals 5 points in here. I could not place a point on the center, but I can do anything else. So let's say there is a point over here, point here, point here, point here. And then I'm going to join these points with straight lines to the center of the circle. Okay. Now, the important thing to notice over here is that the angle between the lines that I used to divide the circle into 4 equal parts is at most 2 pi over 4, because the entire angle of a circle is 2 pi, and then I've divided it into 4 parts. So the angle made by each of these sectors is 2 pi over 4. So this angle is 2 pi over 4, this angle is 2 pi over 4, and so on. Now, no matter where I place the 5th point, the 5th point has to lie in one of the 4 regions. So let's say I place that 5th point over here. Now, when I join this point with the center, this angle has to be less than 2 pi over 4, because, well, this entire angle is 2 pi over 4, so that one has to be less than that. So this is the general idea. Now, the way you write it up is as follows. You basically describe this entire process more generally. What you say is that Let's divide the circle C into n equal parts, Then the angle of each part, or the angle subtended by each part, must be at most, or should actually be equal to 2 pi over n, not at most, but it's equal to 2 pi over n. Now, as the circle is divided into n parts, and because I have n plus 1 points by the pigeonhole principle, at least one of these parts must contain 2 or more points. Since the angle, now you can say that since the angle of the entire sector is 2 pi over n, the lines joining at least 2 of these points, or you could say the angle or the lines joining at least 2 of these points, must create an angle which is at most 2 pi over n. And yeah, this will complete the proof. So the one thing that I really like about not particularly this question, but such proof-based questions, is that mostly when students are in high school, they tend to think that maths is just bunch of numerical analysis where you just have a bunch of computations or numerical problems that you have to solve. But then when you make the transition into university, especially if you are someone who will be taking some sort of analysis courses, or you'll be doing rigorous mathematics, you see that there is a lot about mathematics that has very less to do with numerical analysis. It's more about proving theorems, most of which do not normally use a lot of numerical analysis or numerical methods. And that's not to say that those numerical methods are not important, or that computational aspects of mathematics are not important, but just this idea that there is a lot more to mathematics than just computational analysis and stuff. So yep, that's pretty much it. I hope you like this video, and I hope that you'll find this principle useful, in especially your courses about discrete mathematics. And yep, let me know if you have any other questions, any other principles that you would like me to explain. And yep, I'll see you in the next video.